This is section 18 of the M1 booklet, tilting. So we're on page 58 of the M1 notes booklet. As usual, this is video, so you may need to pause to take notes. I won't give you time as I would in a lesson. So carrying on, page 58. Right, so the idea here is an issue of tilting. So we've got a before scenario where we've got, say, a bridge supported in two places and it's balanced. So if we take our anti-clockwise moments, if we take a moment to B, the only anti-clockwise moment will be created by mg. It's y away, so it's mgy. So doing clockwise equals anti-clockwise. The clockwise forces, well, RB has no moment, so there's only one clockwise force, which is RA. It's x plus y away, so x plus y times RA. We have our balanced equation. Now suppose on the edge of our bridge we have someone walks on the side of it with a force F. Our bridge isn't suddenly going to collapse, so it will still be balanced. Now, if we take a moment to B, the only anti-clockwise force still remains to be mgy. And the RA force is still in the same place and the same distance away. So that part of the equation is still the same. But now we also have a F force that's going clockwise, and that's Z away from the point B. So we have Z times F to add along the top of that. Now if we compare these two equations, the before and after, the right hand side is the same in both occasions, and the mass of the bridge hasn't changed and the distance away from the point B hasn't changed. The right hand side is a solid constant. However, since the second equation's got ZF, the only way that could work is if the other term, the x plus y times RA, reduces to compensate. Now x and y are distances that don't change, so it must be the reaction force that decreases. So RA must decrease as F increases. So the bigger F is, the smaller the RA it needs to be to cancel down so they would get the mgy. Now this can continue to the point that RA is equal to 0, but the rod would still be in equilibrium. Then we say the rod is on the point of tilting about B. It's very similar to limiting equilibrium with friction. Basically, any more force would make it tilt, so it's on the point of tilting. So in examples, if we're told that we're on the point of tilting, we need to know that one of those reaction forces is equal to 0, and that allows us to solve the equation. So we've got uniform planks, so the centre of mass in the middle, mass 10 kilograms, length 2 meters, from A to B. So again, a sketch is always a good idea for mechanics. Rests on two supports, C and D, where AC is 0.5 meters. We've got RC, we've got RD, which is 1.3 meters. Centre of mass mean it will be halfway, 1 meter in. And the mass is 10 kilograms, so the weight is 10 times G. We have, so 1.3 is another 0.3 meters in. We have the support D, and then it's 0.7 meters for the rest of the way. So the whole thing adds up to 2. Now we're told the buoyant mass 30 kilograms stands at the plank at the point E. The plank is then on the point of tilting about D. So if it's tilting about D, then the reaction force at C will be 0. Now from experience, the E would have to be somewhere over here. But we're going to have it as a distance from A, because we want the distance AE. We're going to call that x meters. Now, we've got two unknowns, the x, which we need to find, and the rd. Now, if we did a moment equation, we'd have x's and rd in there, so we don't want that. Excuse me. So we'll need to find the RD first before we're able to do a moments equation. Now the only alternative in these sort of questions is to use up equals down to find the missing force. So up is equal to RD, down is equal to 10G plus, and we haven't put the weight of the child there, the weight is, if he's 30 kilograms, the weight is 30G. So RD equals 10G plus 30G gives us a total of 40G. Now we're taking moments. But we need to choose our point carefully. Now we want the distance from A to E, so the easiest place, just like when we're trying to find the centre of mass for a non-uniform plank, is to do our moment about A, so the moment of the boy will be x times 30G. Any other point will make it very difficult to work out what the distance is in terms of x. So for ease, make it easier for us, we'll take our moments about A. Draw our force moment table. So what force have we got? RC we can ignore because it's 0, there's no force there. We've got a 10G force, the RD which is 40G, and the boy which is 30G. Excuse me. The 10G is halfway, it's 1 times 10G, 10G, Newton meters, and it would spin in a clockwise direction around A. The 40G, which is RD, is 1.3 away. So 1.3 times 40G is 52G. Now that one would spin in a anti-clockwise direction. And finally the 30G is x away, so it's 30Gx. And that one would spin in a clockwise direction. So clockwise equals anti-clockwise. 30Gx plus 10G equals 52G. G is in each expression, so we can cancel by G. Take the 10 off. 30x equals 42. Divide by the 30, we get our distance. Which is 1.4 metres, which as I suggested is past there. Let's say if we'd drawn it in the wrong place, it wouldn't have made any difference to the calculations there. And that concludes this section.